Welcome everyone to the Carnegie Summer Student Symposium. I'm super excited today to have with us our 10 undergraduate summer students who have been completing work with a number of advisors. I want to take this opportunity to thank all of the people who have been involved in either the educational program this summer or who have advised students, and encourage all of you who will be here next summer to consider advising a student and start thinking about projects now. We start taking applications from students in January, so it's sooner than you think. Yes, I'm super excited. The 10 students that have been here this summer have completed really outstanding work, and I think you guys are going to be excited to hear about it today. Yeah, it's like one of my favorite days of the year. So, all right. So, starting us off, we have Sandy Moak here, who many of you may recognize. Sandy, she was here last summer as well. This year, she's been working with Steve Scheckman and the rest of the instrument group on upgrading the guider system on Magellan. Sandy is currently taking some classes at PCC, but she got her undergraduate degree already, a BS from CSU Northridge in speech-language pathology, but she's interested now in doing sort of aerospace engineering and those kinds of things, and so she's been taking math, science, and engineering classes at PCC. So take it away, Sandy.
Thank you, Gwen. Thank you. Okay. Hi, everyone. I'm Sandy. As Gwen mentioned, I've been working on a project this summer to help upgrade the guider system on the Magellan telescopes, along with Steve Scheckman, Jeff Crane, and Charlie Hull. So, a little bit about the Magellan telescopes themselves. Most of you may know they are 6.5-meter twin optical telescopes located at the Las Campanas Observatory in Chile. Magellan 1 went on sky in the year 2000, and Magellan 2 went on sky in the year 2002, which means they've been in service for over 15 years, which is motivation enough for us to want to look into upgrading some of the systems on the telescopes. And in this talk and this summer, I'm working on a project to upgrade the guider systems specifically. So the current guider system, I just want to focus on two main components. One is the field viewer tube, and one is the Shack-Hartmann tube. The field viewer tube itself, it allows the astronomer to find a guide star on the sky in order to keep the telescope tracking the sky effectively all night. And it also estimates the seeing measurements going on during the observation run, which is really important to know what kind of data you might be getting out of the observation run itself. And the second component we've been working on is the Shack-Hartmann tube, which is, it houses the Shack-Hartmann lenslet array, which is a specialized lens that has many tiny lenslets on it in a grid pattern that all are identical and have the same focal length, so they all produce a grid of the same image. And the Shack-Hartmann tube houses this array, and it's involved in the active optics system on the telescope, which corrects for mirror aberrations that happen throughout the night depending on, based on temperature changes. And so it corrects for things like astigmatism and different aberrations in the mirror, and it corrects for them using actuators underneath the mirror itself. So that's the active optics system. And the guider system itself, I just want to orient you a little bit about the anatomy of it. There are quite a few things involved. So this unit itself is located, there's two located on the Naismith axes of the telescopes, and depending on which instrument you're using, that would be which guider system you'd be using. And I want to draw your attention to these specific places. And it might be a little bit confusing, but these units are identical. They're just symmetrically flipped. And just to kind of orient yourself as well, these boxes here are the cameras. So we'll be going into more and more detail, but this is starting kind of big, and we'll work our way down. So a little bit more detail about that image you just saw. Again, the camera is located here, and here are where the current guider tubes are, and some hardware over here involved with switching filters out, and also a pickoff mirror that guides the light from the telescope to the guider system. And the main things, as I mentioned before, that we'll be working on are upgrading the optics in those guider tubes. And here's the proposed changes that we'll be making on the guiding system. So maybe the first thing you might have noticed is that there will be a new camera. So the camera that's on the telescope right now is a CCD camera, and we're looking to upgrade it to a CMOS camera, which stands for complementary metal oxide semiconductor. And it's going to have a much lower noise output, and it will create much sharper images, which is what we really want for this guider system. And so another change that you might notice is that the hardware that was here is now gone, and we are replacing it in favor of a swing arm mechanism, which I'll be going into a little bit more. But ultimately, the optics inside these tubes will just provide better images for the camera to then analyze and overall get better images for the observation. So even more focused in on the guider tubes themselves. So as I mentioned before, we have a field viewer tube, which is the larger of the two, and the Shack-Hartmann tube, which is the smaller of the two, and the camera over here. And here is the swing arm mechanism that I'd mentioned. We'll be going further into that in just a few minutes, but I just want to let you know exactly what we'll be upgrading and how it will affect the astronomer and how it will affect that night's observations. So with the new optics configuration, we will be able to, with the new optics and the new camera configuration, we estimate that we'll be able to see guide stars that are on a magnitude fainter than currently found. So that just means we'll be able to find more guide stars in your field of view when you begin observing, and to get a guide star easier to keep the telescope on track. And also I'd mentioned that the field viewer tube is responsible for giving you a measurement of your seeing for that night, and we estimate that the new camera and optics will allow for 2 times better accuracy in the seeing measurement. So you'll just be able to better estimate what kind of data you'll be getting, which is really important and really useful. And secondly, the Shack-Hartmann tube, as I mentioned, is involved in the active optics system. The new Shack-Hartmann lenslet array is manufactured in a much more advanced way than it was when it was first put on the telescope. So we'll be using a new micro lenslet array, which will create smaller and sharper images for the camera to analyze. And this is important because this is the kind of image you would get from the Shack-Hartmann lenslet array. And the reason that you're not seeing the full grid here is that this is what the primary mirror sees. And there's no light that gets to the mirror because in the center that's where the secondary mirror is and the housing for the secondary mirror, so light doesn't quite get to the center here. But each point of light represents a location on the mirror, and that's important because once we have proper calibration for where the points of light should be, we're able to tell how the mirror is aberrated and how it deforms throughout the night and be able to correct for those, which is very important in maintaining good images. So back to this to reorient yourself. Now we know a little bit more about the field viewer tube and the Shack-Hartmann tube. I just want to go into a little bit about the swing arm here. So this is what it looks like from the front view. The swing arm at this point is disengaged and the field view is in front of the camera. So the light will be coming in through here, going through the field viewer and to the camera. And at this point, again, the swing arm is up, and so none of these mechanisms are in place for the field viewer. However, when the swing arm is engaged, we're able to, we have an aperture, a small aperture for the Shack-Hartmann tube to allow starlight in. And then also we can use an LED and pinhole to calibrate the lenslet array itself. And this will give a point of light that's at the center of the lens, which is where we want all images to be. So this would be an ideal situation, and we have that for calibration purposes. So that's how the swing arm mechanism will work. In order to create something solid from a design, there's always going to be imperfections, and we had to account for this when we were thinking about what kind of tolerances we can allow for and not have to give up image quality in its place. So this is a really gross representation of what it might look like this is the optical design for the field viewer as created by Steve Scheckman. And if we move this large aspheric lens off the optical axis by 2 millimeters here, which is really gross and we wouldn't want to do that, you'll notice that up here when the lens is on the optical axis, the images are right on the detector where we want them and the quality is good. But when the lens is moved off axis, the images are not even on the detector and it's really not good. So we had to go to the most critical lenses and the critical parts of the optical designs and make sure that the tolerances we can allow for were able to be done on the machines themselves. And speaking of the machines, this is the lathe machine that created the tubes. It uses a boring mechanism, a boring tool, to bore out material from the inner solid metal tube, and it has high precision, high concentricity, and it's very symmetric. And so this is the machine that was used to create the tubes themselves. And they have been machined as of last week. And so here are the tubes, the larger field viewer tube and the Schack-Hartmann tube. They've been black anodized to reduce reflections from the light that actually goes through them, and also it helps protect the material itself. And here's a spacer that will go between lenses, and this little washer will house the Schack-Hartmann lens as well as a filter. And there are also some inserts here that go inside the tubes which house more lenses, and those are also created to high precision with the lathe machine. And so once we had the machined parts themselves, we had to continue with our tolerance analysis. So once we had the physical pieces, we used the height arm gauge to make sure that all the critical gaps, the optically critical gaps in the tubes were to a tolerance that was acceptable, and we found that everything was to very high precision and very acceptable, and their tubes are all really great. And so in order to test the optics within the tubes themselves, we have to have a light source. And this is the projector mechanism as designed by Steve Scheckman that I set up in the electronics lab upstairs. The idea is that the light comes in through the right side through this opal glass, which produces an even and diffuse light source. And it goes through two lenses here and out through these Ronchi rulings, which effectively collimate the light, and they simulate the light from the telescope, which is what we want. That's the light that's going to be coming to the guider tubes. And also just focusing in on this aperture that I created from cardboard, and will do the job just fine. This is another thing we measured in the Zemax optical program, and we measured a 13.68 millimeter aperture to reduce stray light, and this gives us the optimal rays that we want for our images. And one of the last steps is gluing everything together. So we've begun doing that, and it's one of the reasons why I don't have the tubes here to show you. We have some lenses setting in the tubes as of right now. So the gluing process, there's kind of two stages. There's gluing the lenses in the tubes themselves, and then we also have to glue some lenses together, and we also have to do that when they're very centered, which is a very delicate process. The optical glue must be made optically appropriate by reducing the bubbles inside of it, and this is what this machine, or this vacuum pump is for, and bell jar as well. A beaker of glue is placed in the bell jar, the vacuum pump turns on, and the bubbles expand, and we do this several times until there are no more bubbles so we can use the glue effectively. So the work that's still to be done, as I mentioned, we need to center the lenses and glue them together, glue all the rest of the lenses into the tubes, and then set up the tubes with the projector upstairs and the cameras at the very end to compare the images of the old CCD camera with the new CMOS camera. And ultimately our goal is to use the new optics and the new optics to maintain smaller images, so we can utilize the really small noise on the CMOS camera. And I just want to thank everybody at Carnegie for being here today, and also specifically Steve Scheckman for advising me through this program, and Gwen Rudy for organizing the summer program, which is a great success.
All right, questions for Sandy?
Yeah.
Josh?
So what's the timetable for having this installed in telescopes?
I believe by December they want to have it on the telescopes.
Any other questions for Sandy? Josh?
So you mentioned that this is going to improve the accuracy of the seeing measurement by about a factor of 2.
Mhm.
Is there an estimate of how accurate the seeing measurements currently are?
I was thinking about this myself. I mean, and I was thinking that they're 2 times worse than they might be. But specifically, I don't have a number for you, but that is a good question. I'd like to know myself.
All right, any other questions for Sandy?